We've spent a lot of time looking at whether a molecule is polar or not. And we want to bring that back to the reason we were looking at it in the first place, which is we know that if molecules have strong intermolecular forces, it's going to affect their physical properties like boiling point, melting point, vapor pressure, and surface tension. And we learned before we took that little aside that there are primarily three types of intermolecular forces in covalent compounds. I'll stress that. We're talking about covalent compounds. We're going to talk about the others soon. They are hydrogen bonding, which we haven't talked about, dipole-dipole interactions, which is the only thing we've talked about so far, and we're about to turn our attention to the London dispersion forces. Now, I want to remind you that hydrogen bonding we think is the strongest, right? It's the strongest of the type of intermolecular forces. So here we're going to be talking about, when we talk about London dispersion forces, the weakest of them all, which is, you know, sort of my analogy to the Lilliputians, right? They're really, really weak, but if there are a lot of these weak intermolecular forces, they can account for quite a bit, and you could actually have a compound that has a higher boiling point with only London dispersion forces than another compound that actually has some dipole-dipole interactions or maybe even hydrogen bonding. So let's see what a London dispersion force is and how that could possibly occur. Well, in order to understand this, let's do a little bit of a comparison here between London dispersion forces and the dipole-dipole forces we've already done. So I'm going to throw me up there, and let's look. We got to get these things going. So this is a really nice simulation of polar molecules interacting through a London dispersion force. And what I like about this moving image is that you can see that the purple end might be the, let's say, positive end, the red end might be the negative end, and you see how they line up so that those positive and negative ends interact for those temporary moments when the molecules pass by each other. But they're not strong interactions. We're talking 20 kilojoules, maybe 10 kilojoules. So if there's a high enough temperature, then obviously you can break those intermolecular forces and separate them. But there's no way that you could actually break the bond at that sort of a temperature. So imagine a good example of a polar compound that might look like this is hydrogen fluoride, right? Hydrofluoric acid. Because fluorine is much more electronegative than hydrogen, there'll be a permanent dipole where you separate the partial and negative charges. They're still partial positive and negatives, but they're going to be set up that way permanently. And so it'll be able, it's an example of a molecule that could interact in the way that this diagram is showing through dipole-dipole interactions. Now, what are London dispersion forces? Well, let's look at fluorine. So if you imagine fluorine, which is a non-polar compound, it does not have an uneven distribution of electrons. It does not have a partially positive and negative side. So you might think there's no way for these two to kind of be attracted to each other, to have those sticky forces, right? That's not an official AP word. Don't ever use sticky forces. But you get what I mean, right? Yet there must be some sticky forces. Because hydrofluoric acid, yeah, it boils a little bit above room temperature, right? 273 is room temperature. But fluorine actually has a boiling point too. It's a lot lower than room temperature. It's very cold, but yet it has a boiling point, which must imply that if this diagram down here was meant to represent two fluorine atoms, see them wiggling, this diagram suggests they have no attraction whatsoever to each other. They're just randomly bouncing around, yet it has a boiling point. They must be able to do some sort of attraction in the way the dipole-dipoles are. This can't be accurate. So how is that possible? Well, it's because they do have an attraction. It's a very weak attraction, and it's called a London dispersion force. Let's get to how. Well, another example would be a neon atom. Now, neon's not diatomic, it's just an atom. So this represents its nucleus and its electrons flying around. You might say, could it be attracted to another neon atom? But if they're atoms all by themselves, they don't have a more electronegative partner that's trying to pull electrons away from them. You would think their electrons have to be very evenly distributed, so how could they possibly be attracted to each other? So you're going to see a theme with London dispersion forces. Is in non-polar molecules like fluorine or individual atoms that don't have a dipole, London dispersion forces is the only way that they can have an attraction for each other. But you better believe they do have an attraction for each other. Even neon has a boiling point, which implies it can condense and make itself a liquid, and it wouldn't be able to do that if it didn't have some sort of attractive forces. I think this is a pretty good model for neon, right? Neon's an isolated atom, but you can see the neons have sort of that stickiness for each other, and that's because they do have an intermolecular force. It's not a dipole-dipole force, it's a London dispersion force, and it's much weaker, but it's there. So how does this London dispersion force work? Well, let's simplify things a little bit and drop from like neon, which has a lot more electrons, has 10 electrons, down to just helium. And let's imagine helium's 2 electrons. Now this little moving image is not showing its nucleus. It's showing just its 2 electrons. And electrons we imagine as flying about the atom, right? And when they fly about, they may have these moments where they aren't so evenly distributed. Like right there, did you see for a moment they were on the right side? Now they're pretty evenly distributed. But right there, they're on the right side again, which is going to make for a fraction of a second this side negative and the other side positive. You can see it's going to be constantly fluctuating in this way. So it's not going to have that sort of setup permanently partially negative and partially positive, and it's going to have a temporary dipole. And if it were to run across another helium atom that was in a similar situation at that moment, for that fraction of a second, if this one's electrons are down here on this end and the other ones are down there on the other end, they will have a momentary attraction. So what a London dispersion force is it's a temporary dipole. So they're going to be weak because they only last for fractions of a second. They're weak because molecules do not have permanent dipoles when they're nonpolar. But I want you to understand something about the second molecule. The second molecule, actually, it doesn't have to be a random chance that they have their electrons lined up so that they are attracted to each other. It turns out that the very first one, so let's imagine if we have an atom that has a nucleus here and it has these electrons evenly spread out, and for a moment those electrons are more on this side over here. That means for a moment this side is going to be negative and that side is going to be positive, right? Imagine that is my atom right there. Now, the one next to it, you might think, does it randomly have to be set up so that it can be attracted to this one over here? And the answer is no. The fact that this one is negative, you can imagine if its electrons are initially evenly distributed, the negative side over here is going to repel these electrons and push them to the other side, so that they end up over here. And that's what we refer to as an induced dipole. So yes, the first one is kind of a random fluctuation of electrons, right? But when it has that momentary dipole where the electrons are on one side, it will induce a dipole in the one next to it. And then the positive and negative ends can be attracted to each other. Now you know this is going to be random. It's going to be for short periods of time. It's not going to be long lasting, and that's why these are particularly weak. So, to wrap that part up, London dispersion forces, which incidentally you may see them called van der Waals attractions. Well, all molecules have London dispersion for intermolecular forces because the only thing you need to have a London dispersion force is an electron cloud that's willing to be a little bit movable, right? But they're especially important for nonpolar molecules because nonpolar molecules, those are the only intermolecular forces that they can possibly have. They don't have permanent dipoles, so they can't do dipole-dipole. We're going to find out they can't do hydrogen bonding either. The only thing that nonpolar molecules can do is London dispersion forces. But it's important to understand that even polar molecules can do this type of intermolecular force. So examples of molecules that can only do London dispersion forces. Chlorine, right? You have 2 chlorines. There's no dipole. It's nonpolar. It's all it can do. Fluorine, nitrogen, right? All good examples. Nonpolar molecules. Argon, any noble gas because they don't have bonds. But also all hydrocarbons. Because carbon and hydrogen have such similar electronegativity, there's really not much of a dipole between the two of them. So if you had methane, It has nothing but carbon and hydrogen. It can't have dipoles. So these are all good examples of hydrogen and carbon containing molecules that for the most part, the only intermolecular force they can have is London dispersion forces because they're nonpolar. Now I want to mention one last thing about this fluffy electron cloud idea, right? So we don't refer to that sort of large movement of electrons within an atom, random movement, as fluffiness, although I like to think about it that way, as like clouds, right? We refer to those kind of electrons as polarizable electron clouds. So the more electrons an atom has, the stronger the London dispersion forces are going to be. And the more polarizable those electrons, as in if they're very far from the nucleus and they're very fluffy and they can move around a lot, right, you'll have stronger London dispersion forces there. So if we were to look at, like, say, just the noble gases, which one of these compounds do you think would have the strongest London dispersion forces? Well, definitely radon, right? Radon has a massive electron cloud. Those outside electrons are so far from the nucleus that the nucleus isn't going to be able to hold them really tight, so they're going to be very fluffy. They're going to be very polarizable. And the more electrons you have, the stronger the London dispersion forces. And the more polarizable those electrons are, the stronger the London dispersion forces. So I'm a little bit sad that I didn't look up the boiling points, but I'm willing to bet you radon would have the highest boiling point. But we certainly know helium is a gas, neon is a gas, and somewhere right in here they start to, well, I think those are gases too, but they're very dense. But somewhere down in here you start to turn into non-gases, right? And it's because they have much stronger London dispersion force intermolecular forces. If you were to look at the halogens, right, which are all diatomic molecules, doesn't matter that they're diatomic molecules. If you look on a periodic table, iodine has many more shells of electrons. And so I2, instead of having just, say, let's see, fluorine has 18 electrons total between the two of them, 9 each. Iodine actually has 53 electrons in each atom. That's a lot of electrons, a lot of movability, and so there's going to be a lot more fluctuation in its electron cloud, and it will have much stronger London dispersion forces in its attraction to other iodine molecules. So let's try this out. Which of these two will have stronger London dispersion forces? Ethane, which is a nonpolar molecule, or propane, which is a nonpolar molecule? Well, the answer is definitely propane. Why? Because propane has 3 carbons and a whole bunch of hydrogens. All of those carbons and hydrogens have electrons in them, and they happen to have more electrons than ethane does. Ethane would look like this. Less carbons, less hydrogens means less electrons. Less electrons means weaker London dispersion forces. Now, neither one of these compounds could do dipole-dipole interactions because they're nonpolar, because they're hydrocarbons, but definitely propane would have the strongest London dispersion forces with its neighbor. Now, you notice I haven't drawn a London dispersion force. Remember, that would be an attraction between it and another one of those molecules. Forgive me for not drawing it out again, but right, it's that. This is the London dispersion force, which is just a type of intermolecular force. Let's look at the effect of branching. Now, if you're looking at branching and you had two compounds that had the exact same number of electrons, and the reason I know these two have the exact same number of electrons is both of these compounds have 7 carbons and 16 hydrogens. If you count them up, they should be. I'm hoping. I'm not going to count them up, but I believe they should be. These two compounds are isomers of each other. Isomers are compounds that have the same formula but different structures. Now, if you were to look at these two and you were trying to figure out which of these two would have stronger London dispersion forces, well, the answer is that this one over here has stronger London dispersion forces. Why? Well, it has to do with how close that those molecules can get to each other. London dispersion forces are weak forces. They can't act over very long distances. So if you think about this molecule down here, it's pretty flat. I think I might have the right number of carbons. 1, 2, 3, 4, 5, 6, 7. And another one would be able to shimmy up right next to it, right? It's like two snakes spooning. A little bit of an awkward thought. Snakes can get really close together. There's a lot of surface area they can touch there. And so these weak London dispersion forces that would occur between this thing all the way down its chain through all of its electrons, all those temporary dipoles would be able to get very close together. But if you make those London dispersion forces act over a long distance, it's just not going to work out. Like if you had two of these things, they're like all crookedy kind of things, right? Oop, I might have put too many carbons. But you can imagine if another sort of crooked one tried to come up to it, well, it's like, have you ever seen two Christmas trees hug? Neither have I, because it's an awkward experience. Christmas trees don't hug very well because they're all prickly and they just can't get together. Their surface areas don't overlap very well, which makes their London dispersion forces act over much longer distances. And so therefore they have very weak London dispersion forces with their neighbor. The more branching there is, the less surface area, the further away those LDFs have to act, and the weaker they're going to become. So straight chains always work better than branch chains. And of course, the longer the molecule, the more electrons you have in it, the more London dispersion forces you can have. All right, so we're going to do a couple of questions to see if you grasp this idea of London dispersion forces, and then we'll continue on to hydrogen bonding in the next lesson.